Okay, good evening, everyone. Okay, so just time check. It's already quarter to seven here in my watch. Okay, so maybe we can now start. Um, I believe this is now our last lecture, I think. Okay. Um, so I understand your final exams is already coming up soon. Okay. So I guess from here, the rest of the remaining time, you can just devote it to further discussions with my colleagues, no? Okay, in preparation for your final exam. Okay, but I think as far as I'm concerned, I think this is my last topic. Okay, for the course. Okay. So so I hope everyone can hear me well. Okay, if you have any concerns, please call my attention as soon as possible. Okay. Okay. So let me just share my slides. Okay. Okay. So for our last topic, let us try to discuss a little bit about lateral earth pressure. Okay. Um, So lateral earth pressure is used in trying to analyze retaining structures, okay, such as retaining walls. In the undergrad, normally we are taught the designs for retaining walls, okay, concrete retaining walls, okay. So in the before you can design the retaining or the concrete retaining wall, first we need to know the forces acting behind the retaining wall. Okay, or normally retaining walls can be used to support backfill materials. Okay, that this can also be used or the earth pressure forces can also be used to design the basement walls. Okay, for example, in high-rise buildings where you have basement walls. Okay, you have basement one, basement two. Like for example, this basement parking. So it has walls. Okay, so you can also use this concept. Okay, so these are commonly found in foundation engineering as they support slopes of earth masses. Okay. So the proper design and construction of these structures would require a thorough knowledge of the lateral forces that act between the retaining structures and the soil masses being retained. Okay. Um, so these lateral forces are what we call or are caused by lateral earth pressure. Okay. So, for example, if you want to build a house, for example, and then your maybe your land, okay, is quite sloping, then you need to cut some area for you to build your house, for example, or any structure, and then aside from cutting the slope, maybe you found out that okay, you still need enough space, okay, for your house, so then you can maybe do some backfilling works. Okay. So for the backfilling works, then you need to protect. No, you need to support such backfill material. Okay. So one structure can be this retaining walls. Okay. Normally around 5 meters height. For example, um, concrete retaining walls might still be okay. No, in terms of cost, for example. But higher heights, yeah, maybe you can think of other options already, no? Such as mechanically stabilized earth walls, no? For example, using geosynthetics, okay, which we have done in some of our projects as well. Okay. So for the moment, we can probably think of concrete retaining walls, no? Okay, say around 5 meters. So the magnitude and distribution of the lateral earth pressure depends on many factors, such as the shear strength parameters of the soil being retained. I think we have discussed this last meeting. Okay, the shear strength parameters. Okay, if you still recall, you have the cohesion and the friction angle. Okay, these are the shear strength parameters. Okay, it may be total shear strength parameters or effective shear strength parameters. Okay. And then we also have the inclination of the surface of the backfill. It may be inclined or normally it is flat. Okay, for you to build a structure. Okay. And then we also have the height and the inclination of the retaining wall at the wall backfill interface. Okay, and as well as the nature of the wall movement under lateral pressure, whether it is active movement or it is passive movement. When you say active movement, that means the wall is moving away from the soil. When we say passive movement, that means the wall is moving towards the soil, for example. Okay, or the wall may not move at all. Okay, so it depends on the nature of the wall movement. Okay, as well as the adhesion and the friction angle at the wall backfill interface. Um, so unless the wall is, if we can assume that the wall is frictionless, okay, so there is no adhesion there. Okay. Okay. So to discuss further on this lateral earth pressure, we can probably consider this figure here, okay, figure A, wherein we have a frictionless wall AB. Okay, so this is a frictionless wall here. Okay, so addition values are maybe zero. Okay, um, then this retaining wall has a height of h. Okay, and then we can probably consider a soil element. Okay, we can consider a soil element at any depth z, at any depth z um, from the ground surface. No? So this is now your horizontal ground surface. Okay, so so in that soil element that we have just seen earlier, located at a depth z. Okay, if you see my cursor, so that element, okay, so this element here, okay, is subjected to a vertical effective pressure, okay, for that frictionless wall. Okay, for the moment, let's consider a frictionless wall, okay, because as sometimes the wall can have frictions, no? It can have friction itself, you know, between the wall and the soil. But for the moment, to make things simpler, let's just assume that we have a frictionless wall. Okay. So the soil element we have just seen here, okay, that is located at the depth z, that's any depth z, is subjected to a vertical effective pressure, okay, or a vertical effective overburden stress. It's just the same. Okay. That's your sigma prime sub zero. I think we have already seen this parameter in our previous lectures. Okay. And then, aside from the vertical effective pressure, you also have this horizontal effective pressure, sigma H prime. Okay. So, in for the soil element, let us assume that there are no shear stresses. Okay. Let us consider that there are no shear stresses on the vertical and the horizontal planes of the soil elements. No? So that means there are no shear stresses here on the planes of the soil element. So we only have normal stresses perpendicular to the surfaces of the soil element. Okay. Okay. So the ratio now, okay, between the horizontal effective pressure, that's sigma H prime, to the vertical effective pressure or the overburden pressure, okay, or the vertical effective um, um, overburden stress. Okay, so the ratio between these two can be given by a non-dimensional quantity k. Okay, so with respect to this non-dimensional quantity k, there are now three cases that we can consider with respect to the retaining wall. So the first case is when the retaining wall is static. That means there's no movement either to the right or to the left of its initial position. Okay, so that means the wall is in static equilibrium. So, for example, this one here. The wall is in static equilibrium. So, in that case, the horizontal effective pressure can be referred to as the at rest earth pressure. Okay, that means there's no movement in the wall. Okay, so that means you have a condition of at rest earth pressure for that frictionless wall. Okay, so in that case, the K can be given as K sub O. Okay, where K sub O is now considered or is now called the at rest earth pressure coefficient. Okay. Okay. Now, for the second case, so in this case, the friction wall or the frictionless wall rotates sufficiently about its bottom to a position of A prime B. Where is that? Let's see. Okay, so that's this. This is now your A prime B. Okay, so from the initial position of the wall, okay, from here. Okay, so from the initial vertical position of the frictionless wall, then this time the wall now has some movement of say delta L sub A. Okay, A means yeah, active. Okay, so from AB, so you now have movement A prime B. Okay, so in that case, if the wall now rotates, then a triangular soil mass ABC prime, adjacent to the wall, will reach a state of plastic equilibrium. Okay. And will fail sliding down the plane BC prime. So where is that in the figure? Okay, so that's actually, sorry, that's actually A, B, C prime. So this is a soil mass. Okay, so the soil mass will reach a state of plastic equilibrium. So that when you say plastic equilibrium, that's on the verge of failure. Okay, yeah. So basically, in slope stability analysis, there is what we call a limit equilibrium equations. So this limit equilibrium equations is actually based from the plastic equilibrium behavior. Okay, wherein the equations are derived considering that the soil mass is on the verge of failure. That's what we mean by plastic equilibrium. Okay? Okay? So at this time, the horizontal effective stress, okay, or sigma prime H, will now be equal to sigma prime sub A. Okay, where sigma prime sub A will be referred to as the active earth pressure. Okay, so from this formula from the at rest earth pressure, okay, so since there is now wall movement away from the soil, okay, with this delta, with this displacement of delta L sub A, this one here, okay, then we now have, or the at-rest earth pressure will now become the active earth pressure. Okay. So in that case, your K will no longer be K sub O, but it will now become K sub A, where K sub A is now the active earth pressure coefficient. Okay. So prime is your vertical effective pressure or your vertical effective overburden stress. Okay, it's just the same. Now, the last case is when the frictionless wall would rotate sufficiently about its bottom, okay, to a position A double prime B. So that's this one here. So this time, from the initial position of the wall, okay, this is now your at-rest position, then the wall will now move towards the soil, okay? Yeah, by a distance of delta L sub P. Okay, so this is now the new position of the wall. That's A double prime B. Okay, okay. So, um, so in this case, then a triangular soil mass, A, B, C double prime, okay, will reach a state of plastic equilibrium and will feel sliding upward. So this time the soil will slide upward along the plane BC prime. Okay. So kanina, the soil will move downwards, na? Kasi moving away man ang atong slope. Okay, moving away. So the soil will slide down. Okay. But in this case, if the wall will move towards the soil, then this soil mass here A, B, no? This A, B, C double prime, this soil mass will move or will slide upwards. Okay? Yeah, along this plane BC double prime. Okay? So musaka, no? Musaka ba natin yuta? No? So in this case, murnao itong yuta. In this case, musaka yung yuta. So in that case, then the horizontal effective stress sigma sub H prime will now be equal to sigma sub P prime, which we can now call as the passive earth pressure. Okay, so from the at-rest equation, then you now have the uh, passive earth pressure, okay, over the overburden stress, okay, and then this ratio is now equal to the passive earth pressure coefficient, no? K sub P. Okay, so that means for the active, so for this one, for the active earth pressure, that's equal to the active earth pressure coefficient times the overburden stress. Whereas for the passive pressure, you now have um, the passive earth pressure is now equal to the um, overburden stress multiplied by the passive earth pressure coefficient. Okay. So again, don't worry about these figures. These are all taken from your book. Okay. So you can just find all these things in your book. Okay. So again, remember that the wall AB here is frictionless. That's frictionless. There's no friction. Okay. So here we just have a figure here on the nature of the variation of the lateral earth pressure with respect to the wall tilt. Okay. Wherein if this is now the earth pressure at rest, okay, then this is now the variation of the wall tilt, okay, the wall tilt with respect to the passive pressure, okay, while this one here is the variation of the lateral earth pressure with respect to the wall tilt, considering the active pressure, okay. So that means, yeah, from this line here, then you now have the ratio of the delta L sub A, where delta L sub A and delta L sub P, that is your basically your movement, okay, delta L sub A as well as delta L sub P. Okay, that's the movement on the wall at the surface. Now, with respect to the bottom. Okay. So, with respect to that movement, okay, that's the ratio, the movement with respect to the height of the wall, with respect to the active earth pressure, as well as the movement of the wall with respect to the height of the wall, considering the passive pressure. Here we can see that for different ground conditions, okay, for example, when you have a loose sand or a dense sand. Okay, so loose sand is an uncompacted sand, for example. A dense sand can be a compacted sand, okay, where we use compactors, or in the case of a soft clay or a stiff clay. A soft clay, you can imagine that the same like when you are in a rice field. Um, can you imagine a rice field and then it's filled with water, then you walk on it, then your feet will be yeah, submerged around knee depth, for example. That can be an example of a soft clay material. Okay. While a stiff clay material is quite hard, no? Such as the clay materials you can find there in some of the slopes in Talamban. Okay, so these are stiff clay materials. No? Normally, stiff clays, if you excavate through that soil, normally they can withstand vertical cuts, okay, for a longer period of time. Okay, that's a visual. This a visual that can be a visual observation of a stiff to hard clay material. Okay, so with respect to these materials, we can see here that the movement with respect to the active earth pressure is a bit larger compared to the movements. No? Okay, with respect to the active earth pressure. Okay, um, so yeah, that's this one here. No? That's what this figure is showing us. No? That the movement in the passive earth pressure condition is larger than the movement with respect to the active earth pressure condition. Okay, so that means this movement seems to be larger than this movement here. And that's what these values are telling us. Okay. Then you can also see that the movement in the loose sand material, okay, is larger than the movement in the dense sand material, which is logical, okay, because you have loose material. And also the movement in the soft clay is larger than the movement in a stiff clay, which is logical. Okay. And then between a sand material and a clay material, the movement in the sand material is smaller than the movement of the wall in a clay material. Okay. So that's why when we consider backfill materials, we normally consider granular materials, no? Granular materials, sandy or gravel materials for that matter. Okay, because it will have a smaller movement with respect to your retaining wall. Okay, so and then um, if you have a smaller movement, then you can design the wall cheaper or less cost. And also, granular materials can have better drainage, no? For example, okay, if water will seep through it. Okay, because it's always best to have good drainage because we don't want poor water pressure to build up within the wall. That can cause wall failure. Okay, so let's just talk a little bit more about this earth pressure at rest. Okay, yeah. So with respect to the earth pressure at rest, okay. So there we have the terms again, the horizontal effective stress. Okay, so let's just go back to the figure. Okay, so you have here the horizontal effective pressure and the vertical effective pressure or the overburden stress. Okay, or the vertical effective stress. This one and the horizontal effective stress. Okay, wherein yeah, this soil can have this follows the Moore column failure envelope, okay, which we defined last meeting, okay, with respect to the cohesion, okay, value and the friction angle value. Okay, this is now your normal stresses. Okay. Mm. Okay, so again, your soil, okay, your soil has a unit weight. For example, if you look at this soil material here, okay, so you have again your wall of height h, okay, then you have your overburden stress, then your um, lateral earth pressure, okay, or the horizontal, no? Okay, or the horizontal earth pressure, okay. Mm, wherein the horizontal earth pressure is can be multiplied or is equal to the at-rest earth pressure coefficient, okay, multiplied by the overburden stress. But the overburden stress, as what we have learned in our previous lectures, is just equal to the unit weight of the soil multiplied by the depth, no, of the soil element. No? So this may be a dry unit weight or a moist unit weight, or it can be an effective unit weight if the soil is below the groundwater table. No? Okay. Okay, so that's this one here. Okay, so that's your unit weight. Okay, so in this case, we have a dry unit weight material, for example. Now, so for the moment, let's just assume a dry unit weight. No, although in reality, there's no such thing as dry unit weight in the field. Okay, you can have maybe moist unit weight, then you can have saturated unit weight. But then from there, you can derive the dry unit weight. Okay, the only time you have dry unit weight is when you oven dry the soil sample in the lab. Okay, so talking a little bit more about this at-rest earth pressure coefficient. Now, according to this guy in 1944, if we have coarse-grained soils, then the at-rest earth pressure coefficient by can be estimated by this empirical relationship. So when you say empirical, that means it's being derived from um, field data. No? Okay, so you measure some data in the field. Okay, and then you try to make correlations. Okay, so that's an empirical relationship. So according to this guy in 1944, he mentioned that the at-rest earth pressure coefficient can be equal to 1 minus the sine of the drain friction angle or the effective friction angle. That's pi prime. Okay? So this is again your shear strength parameter. Okay, so when designing a wall that may be subjected to a lateral earth pressure at rest, okay, at rest, one must take care in evaluating the value of the at rest earth pressure coefficient. Okay, so these guys in 1984, on the basis of their laboratory tests, they have shown that this equation, this equation here, okay, can give a good results if the backfill is loose sand. However, if you have a dense, compacted sand backfill, okay, then that equation may grossly underestimate the lateral earth pressure at rest. Okay? And this underestimation is due to the process of compaction of backfill, which we normally do. No? Okay, so in construction, when you backfill a material, we normally compact no? The material. Okay, so for this reason, they have recommended this equation here. Okay, so as this is now Jakey's equation, then they just added this term where gamma sub d, okay, is the actual compacted dry unit weight of the sand material behind the wall. Normally, we use sand materials for backfill to have good drainage. And then we now have here the gamma sub d min or minimum is the dry unit weight of the sand in the loosest state. Okay. Okay. So this increase of the KO value by this amount no, from this value here derived from this equation. Okay. So that increase which we observe, okay, is basically due to over consolidation. Okay. So when you have a dense material, then that means you have an over consolidated material. Okay. So when you have or when you have stiff or hard material, that's usually an over consolidated material, for example. Okay. So when you have soft to until medium stiff, I guess, you have a normally consolidated material. Now, for this reason, these two guys, Main and Callaway, in 1982, after evaluating 171 souls, okay, in their research, they have recommended a modification to this equation here. Okay, to this equation, they multiply that by the OCR. Okay, where the OCR is the over consolidation ratio. Okay, or again, if you recall, the over consolidation ratio is the ratio between the pre-consolidation pressure, okay, sigma sub C prime over the present effective overburden pressure, or that's your sigma sub O prime. Okay, so that's basically this one. That's your sigma sub O prime. Okay. And then we raise that to a power sine of phi prime, okay, or the effective friction angle. Where in this equation is valid for soils ranging from clay to gravel, for example. Okay. Now, for fine grain, normally consolidated soils, Massarch in 1979 suggested the following equation for the at-rest earth pressure coefficient. Okay, considering this parameter PI or the plasticity index. So most probably here he's referring to clay materials, normally consolidated clay materials. Okay, and then for over consolidated clays, okay, then the at-rest earth pressure coefficient can be estimated by using this formula or the at-rest earth pressure coefficient at normally consolidated condition, and then you just multiply that by the square root of the over consolidation ratio. Okay. So here in this figure, we can roughly see here the distribution of the at-rest earth pressures, which can be zero at the ground surface, then yeah, that can be equal to this amount, maximum amount of at rest earth pressure. Okay, we're in, and if you can see here, if this is now your height h, okay, then the overburden pressure is equal to the unit weight times the height h. Okay, that's this one. So this is basically your overburden pressure, gamma h, okay, for this at the bottom, no? At the bottom of the wall, okay, at a height h. And then you multiply it by the at rest earth pressure coefficient to get the at rest earth pressure, no? At this, at the bottom. Okay. So this is now then the variation. Okay. The variation. So to get now the total force, okay, to get now the total force per unit length of the wall, we call let us call that P sub O. That's the total force per unit length of the wall. Why is it total force per unit length? Okay, let's see. This is unit weight. That's let's say kilonewtons per cubic meters multiplied by h squared, so the square meter. So then you have kilonewtons per meter. So that's force per unit length, no? Per meter of wall. Okay. So to get now the total force, we just simply get the area of this pressure diagram. Okay. So the area of this pressure diagram is just one half of, okay, this is the area of the triangle, which is one half this earth pressure multiplied by H. Okay, so that gives you one half the at rest earth pressure K sub O gamma H, then multiplied by H. So that becomes H squared. So this is just the area of the triangle. No, it's just the area of the pressure diagram. Okay, so that means this is now your PO. No? Okay, this arrow here. This is now your PO. Okay, that's your PO. That's the total force per unit length of wall. Okay, and then I think we have learned this before, that I think for the centroid of a triangle, it is located at one third of this height, no? From this point. Okay, so one third from this point, and then two thirds from this point. Okay, so you can just recall your engineering mechanics. No? That's with respect to centroids. Okay, okay. So yeah, so earlier we have here a soil condition with no groundwater level. Okay. So in such case, in reality, that can happen. But in some cases, you can have a groundwater level. You can consider a groundwater level. Okay. So in that case, then let's try to discuss now the earth pressure at rest. Okay, earth pressure at rest for a partially submerged soil. That means you have a groundwater level. Okay. So, for example, this one here, you now have your wall. Okay. Okay. So you have your wall here, AB, with a height H. Okay. With a height H. And then let's just divide that into H sub 1 and H sub 2. Okay. Where H sub 1 is the depth of the groundwater level or the groundwater table. Okay. So above the groundwater table, you have the unit weight of the soil. So it did not mention dry, so this may be moist unit weight. Okay. And then below the groundwater table, then you have the saturated unit weight of the soil or gamma sat, which is normally higher than the moist unit weight or the dry unit weight by orders of magnitude of say around 2 to 4. Okay, for example. Okay, so saturated unit weight is heavier, okay, than the dry or the moist unit weight. Okay, so in that figure, let us assume that there is no compensating water on the other side of the wall. Okay, so that means there is no water here. No? Okay, no water. So that means there is no passive earth pressure. Okay, so we only have here um, some um, active pressure, if there is wall movement, for example. But for the moment, let's assume the wall is not moving. So this is just at rest earth pressure, K sub O. Okay, because for active earth pressure, this is K sub A. For passive earth pressure, this is K sub B. Okay, so if we now consider any soil element at a depth Z, at a depth Z, where depth Z can be any depth from the ground surface. Okay, so this one here, depth Z. Um, so for all values of Z less than or equal to H sub 1, that means for all values of Z above the groundwater table, okay, so that's within H sub 1 or less than H sub 1, okay, then the lateral earth pressure at rest, okay, can be given by this equation here, okay, where that is K sub O times the, this is now your effective overburden pressure. That's the unit weight times the depth Z, okay, wherein the variation of this one here can be given by this one, by this triangle ACE, ACE. Okay, wherein in this triangle ACE, the maximum earth pressure is equal to K sub O times gamma H sub 1. Okay, where gamma H sub 1 is your overburden stress, okay, gamma times H sub 1. Then to determine the horizontal effective pressure, this amount here, you multiply it by the earth pressure coefficient. If the wall is not moving. Okay. Okay. Now, if the depth, if we are now considering depths greater than H sub 1, that means we are now considering depths below the groundwater table, okay, then the effective vertical pressure or the effective overburden stress, sigma O prime or sigma sub O prime, is now comprised of two factors. Okay, we now have the effective stress and the poor water pressure components. Okay, wherein the effective stress can be equal to the unit weight times H sub 1. That is that's this part here. Okay, that's this one. This part. Okay, then plus. Okay, plus um, gamma prime times the depth z, the variable depth z minus h sub 1. So that means if you go back here, if I consider, for example, this point here, this point here, excuse me, this point here, then this one is equal to z. Okay? That's equal to z minus um, h sub 1. Tama ba? Okay. So if this is now your z, so um, then this depth here from the groundwater table, okay, this depth here from the groundwater table is equal to z minus h sub 1. Okay, so that's now your Z minus H sub 1, then you multiply that by gamma prime, gamma prime. Okay? Um, where gamma prime is equal to the saturated unit weight minus the unit weight of water. That gives us the effective unit weight, if we can still recall. Okay. So that means the effective lateral earth pressure at rest, okay, um, is now equal to the effective overburden pressure. That's this one here, okay, or that's this one. Multiply that by the um, at rest earth pressure coefficient, okay, and then this variation here. Okay, this variation can be provided by this diagram here. Now, this CEGB. No? That's this one here. Okay. Okay. So that's the this is now your if effective stress. Okay, this is now your effective stress component. Okay, and then you also have here your pore water pressure component. Okay, now for the pore water pressure component, that's again your Z minus H sub 1. That's again that's the depth from the groundwater table down. Okay, that's Z minus H sub 1, then multiply that by the unit weight of water. Okay. So again, the variation of the pore water pressure can be given by this pressure diagram here. Okay. So for this pressure diagram here, for the effective stress, then you now have um, so this horizontal pressure here is now equal to K sub O gamma H sub 1. That's this one here. That's until here. Then plus this horizontal earth pressure, which is now equal to K sub O gamma prime H2. Okay, so for this one, huh? Okay, that's your, this is the additional, huh? K sub O gamma prime times H sub 2. That's the additional effective stress. Okay. And then for the pore water pressure, then the maximum horizontal pressure here is the unit weight times H sub 2. This one here. Okay. Okay. So that means the total lateral earth pressure um, for the earth, okay, and water. Okay, that's the for the vertical for the effective stress. No? Okay, for the effective stress and the pore water pressure at any depth z greater than h of 1. That means below the groundwater table. Then that will be now equal to the horizontal effective stress. Okay, plus the pore water pressure. Okay, wherein the horizontal effective stress can be given by this one here, which we have just derived, let's say from here, okay, this one here, okay, and then plus the pore water pressure given by this one. So we just add that here, okay. So that gives you this total value for this um, horizontal earth pressure at the bottom of the wall. Okay. So initially you have this horizontal earth pressure until the groundwater table. Okay. Then from here it will increase further, adding the effective stress plus the pore water pressure. Okay. So considering this condition here, we would like to derive now the force per unit length of the wall. Okay. So for the force per unit length of the wall can be found from the sum of the areas, okay, of the pressure diagrams. Okay. So yeah, we can pressure diagram one. I hope you're seeing my cursor. This is one diagram. Then this one here can be another diagram where you create a rectangle, and then you have another pressure diagram here, a triangle. Oh, okay. So basically, the sum of these two pressure diagrams is just equal to this one here. Okay. So if we try to go back here in this two pressure diagrams, then we can probably add this pressure diagram one, this one here, this triangle. Then this pressure diagram two, this rectangle here. If you are seeing my cursor, I hope you're seeing my cursor. This one here. Then pressure diagram three, this triangle here. And then the fourth pressure diagram is the poor water. It's due to the poor water pressure. So if we sum up this pressure diagram, so we just get the areas. No? We just get the areas of each pressure diagram. So the first one will be that's one half this one here, which is K sub O gamma H sub 1 multiplied by H sub 1, this height here, which gives you, which would give you this one here, okay? One half K sub O ACE. Now the next one will be area CEFB. That is area CEFB, not this rectangle. So the area of this rectangle is just equal to um, what's the area again? That's K sub O gamma H1, which is this one, multiplied by H sub 2. Okay, so that will give you this area here. Okay, this is the horizontal pressure multiplied by the height H2. Okay, now for this one is just the areas for EFJ and IJK. Where's that? That is okay, that's EFJ, that's the area of this triangle, plus the triangle IJK. Now this triangle. So these two triangles. Okay. So that means we have um, the area of this triangle will now be, so this one here, sorry, this one here is K sub O. That's a K sub O gamma prime H sub 2. Okay? That's a K sub O. This one here is K sub O gamma prime H sub 2 times H sub 2, this height, okay, times 1 half. That's your area of the triangle. So that's 1 half H sub 2 times this length here is equal to K sub O gamma prime H sub 2. That will give you this one here. 1 half K sub O gamma prime H sub 2 squared. Okay, because that is H sub 2 times H sub 2. Okay, and then for the area of this triangle, that's 1 half H sub 2. Again, this is H sub 2 times the unit weight of water times H sub 2. So that gives you 1 half unit weight of water times H sub 2 squared. Okay, so this one here will now give you the force, the total force P sub O per unit length of the wall. Okay, this unit length is say perpendicular to your screen, for example. No? Okay, if you have your laptop with you that's perpendicular to your screen, that's the unit length of the wall, not per unit length. Okay, so that's the unit length perpendicular to this diagram, not perpendicular. Okay, so this can be now the formula if you have a groundwater level. No? So it would be much simpler if there is no groundwater level because you only have this for your total force per unit length. No? So yeah, so it would be nice if there is no groundwater level. Okay, so that means your wall will become more expensive if you have the presence of groundwater level because if the total force will be higher, no, or will be greater. Okay, that will be exerted on the your retaining wall. Okay, so far we have discussed retaining walls wherein the wall will not move. Okay. Um, Now, in practice, we normally consider wall movement, for example. Okay. Um, so that's why in practice we normally provide the active earth pressure coefficients as well as the passive earth pressure coefficients in the geotechnical report. No? For example, if you see that there is a need to do some backfilling works, okay, wherein you need to design a retaining wall. Say, for example, if it's say around less than 5 meters, okay, maybe concrete retaining wall is still okay. So then we can provide, okay, the earth pressure coefficient. Okay. So let us now talk about this active earth pressure. Okay. Then later the passive earth pressure. Okay. Now, so again, the phrase plastic equilibrium in soil refers to the condition where every point in the soil mass is on the verge of failure. Okay. This is different from elastic equilibrium. Okay, yeah, elastic equilibrium. So here, the soil mass is on the verge of failure. Okay, normally for soils, yeah, we consider plastic equilibrium. Okay, now this guy Rankine in 1857 investigated the stress conditions in soil at a state of plastic equilibrium. Okay, so, so that can be seen here in this figure. Okay, so you now have here your wall again, the same wall AB, but this time you now have some movement away from the wall. Okay, so let us now consider the soil element in that condition at any depth Z. Okay, wherein the soil here has a unit weight of gamma and it follows a failure envelope, considering the Moore column failure envelope, C prime plus sigma prime times the tangent of phi prime. Okay, so that means this soil, when it fails, it follows this Moore column failure envelope. So again, we now have here our vertical effective pressures or the overburden stress and the horizontal earth pressures or the horizontal effective pressures. Okay. Now, considering the active state, okay, initially, if the soil is at rest earth pressure condition, then that is symbolized by this circle A here. Okay, the circle A, wherein in the circle A, this coordinate, okay, in the abscissa is now your um, sigma prime, sigma sub O prime. That's your vertical overburden stress. Okay, and then the at rest, okay, horizontal earth pressure, okay, is equal to this point here in your circle, which is now equal to K sub O times sigma sub O prime. Okay, so that's this point here in the circle A. This is now your circle A. So this is now the condition um, in your Moore circle, in your Moore circle, um, considering at rest conditions. Okay. Now, if the wall will start to move away from its initial position, then the horizontal earth pressure here in the soil mass will start to decrease, no? Because they will loosen up. Okay, they will loosen up, so they will start. The horizontal earth pressure will start to decrease. So that means from the initial position of your Moore circle. Okay, so from this point, the vertical effective pressure is still the same. Okay, this point here, but the horizontal effective pressure will start to decrease. It will start to decrease until such time that it will have a the final value at this point here. Okay, which we now call as the active earth pressure. Okay, the active earth pressure. So if this is now your active earth pressure, then you now have your second uh, Moore circle here. Okay, the second Moore circle. Okay, and then you can now have your failure envelope tangent to the Moore circle, to the bigger circle, which is equal to this formula here, which we have just seen in our last lecture. Okay, wherein this failure envelope now has an angle of phi prime from the normal stress axis, and then it has an ordinate of C prime, okay, or the cohesion and the friction angle with respect to the shear stress uh, ordinate axis. Okay. Okay. So in that situation, then that is now being represented by the Rankine's active state. So this one here. So from this circle here to this more circle, this behavior due to the movement of the wall away from its original position, then that can now be considered as the Rankine's active state. Okay. And then the effective pressure sigma sub A prime on the vertical plane, which is considered the principal plane, this one here, the vertical plane, okay, which is considered the principal plane, is now what we call the Rankine's active earth pressure coefficient. Again, please take note, we are considering here a frictionless wall. Okay, frictionless wall. Okay. So next, let us now try to derive this um, active earth pressure. Okay, the active earth pressure sigma sub A prime. Okay. So, so we will be deriving that in terms of the unit weight of the soil, the depth of the soil C, and the shear strength parameters of the soil C prime and phi prime. And that's the effective shear strength parameters. So to do that, let us consider the figure here. Okay. So with respect to this Moore circle, it has a radius DC. Let's consider this the radius DC, which is perpendicular to the failure envelope. No? In such a way that you will create a right triangle. This one here is 90 degrees. So you have here a right triangle. Okay. So that means if this is now a right triangle, then we can have the sine of phi prime, this one here. The sine of phi prime is equal to the opposite side over the hypotenuse. So the opposite side is DC, while the uh, that's a CD, the opposite side to this angle phi prime is CD over the hypotenuse AC. Okay, so that's this one here. Okay, CD over AC. But AC is equal to AO, that's this one here. I hope you're seeing my cursor. Thus, AC is equal to AO plus OC. Okay? Yeah. So let us now try to replace these terms here or these segments here um, with respect to the active earth pressure as well as the overburden pressure as well as the shear strength parameters. Okay. So the radius CD here, okay, the radius CD here can be equal to the radius of the failure circle, or that is equal to sigma sub O prime, that's the overburden pressure, minus the active earth pressure over 2. No? So that's basically the um, the uh, the this value minus this value here. Okay, so that gives you the diameter. Okay, divided by 2 will give you the radius CD. Okay, that's your sigma sub O prime. This is your sigma sub A prime. Okay, so that gives you this one here. And then AO, this AO with respect to phi prime and C prime here. Okay, then just creates a triangle. Then we can have AO is equal to C prime times the cotangent of phi prime. Okay. While OC, this OC here can be equal to um, the average. No? This length here is the average length of the sigma sub O prime plus the sigma sub A prime. That's this length plus this length. You divide it by 2 will give you this length OC here. So that's this one now. Okay. So sigma sub O prime plus sigma sub A prime over 2 will give you OC. Okay. So substituting this one in CD, this term in AO, and then this term in OC, and then equate it to the sign of phi prime will now give you this one here. Okay, this equation. Okay. So again, these are all in your book, no? So please don't worry. So from here, we just cross multiply the denominator on the left side will give us this term here. Cotangent times sine will give you cosine. Okay. So then this one here, this term times sine phi prime will give you this one. So what is left on the right side is this term here. Okay. And then just doing some algebraic manipulations to try to derive sigma sub A prime here will give you this equation now. Okay. Where this equation is your sigma sub O prime times the quantity 1 minus sine phi prime over 1 plus sine phi prime minus 2 times the if effective equation. This one is the effective friction angle. This is the effective overburden pressure. Okay, times the ratio of cosine phi prime, or this the effective friction angle over 1 plus the sine phi prime. Okay, where the effective overburden or where the vertical effective overburden pressure or overburden stress is again equal to the unit weight of the soil times the depth z. Okay, so always remember that. Yeah. Now, yeah, in trigonometric identities, if you still recall our trigonometric identities, this term here is just equal to the square of the tangent of 45 minus 5 prime over 2. Okay. While this term here, cosine phi prime over 1 plus sine phi prime, is equal to the tangent of 45 minus phi prime over 2. Okay, if you try to recall our trigonometric identities. Okay, so then we can substitute this one here. And then this one we can substitute here in such a way that we can have this equation now. And then this one here, we replace it by gamma z, okay, or the unit weight times the depth z will now give you this equation now here. It should now give you the equation of the active uh, earth pressure in terms of the unit weight of the soil, the depth c at any depth from the ground surface, and then as well as the shear strength parameters of the soil, which is the c prime and phi prime. Okay. So the variation of this equation can be shown here. Okay, wherein the maximum value here at the say bottom of the wall is equal to gamma z times k sub a, where yeah, k sub a is equal to this one. Now take note. Okay, okay. Um, let's say for example, if you have for cohesionless soils, no? Say for cohesionless um, soils, okay, where c prime is equal to 0, then we don't have this term. So we only have this term here, for example. Okay. Now, um, K sub A, okay, K sub A can be the ratio of the active earth pressure over the overburden pressure. That's this one here, okay, which can be equal to this term here, okay. Yeah. So that means from this equation here, this can be equal to gamma c times k. This can be replaced, this term here can be replaced by k, considering this equation here. So that gives us this one here, gamma z times k sub a. And minus 2c prime, that's 2c prime, times this one will become the square root of k, because k sub a is equal to the square, okay, the square of tangent. So if you want to get tangent, then you take the square root of k sub a. So that's why you have here minus 2c prime square root of k sub a. Okay. And then there is some part in your wall wherein you have a zero active earth pressure at a certain depth equal to this one here. Okay. And then, yeah, from that inflection point, you have this value here. If you have some cohesion, for example, if you have some clay, if you have a clay material, okay, for example, okay. But if you have a sandy material, then you don't have this term. Okay, so we will start from 0 down to such a value here. Okay, because if there is no cohesion, for example, if you have a sandy soil, for example, a granular soil, for example, where you don't have cohesion, so this one here is 0, and this one here is 0. Okay, so that means this one will go here, this point will go here. So that means you will simply have a triangle. So this one will also be 0. So the maximum value here will be equal to this one here. This just the same as what we have seen earlier. Okay, and then uh, the the failure planes, okay, or the slip planes, okay, this one here. So this can be our slip lanes, for example. So the slip planes can have an angle of plus minus 45 plus 5 prime over 2 degrees with respect to the direction of the major principal plane, which we can see here. This is now your failure planes with respect to the active earth pressure condition. Okay, so if the wall is somewhere here, then this is now your failure plane at a certain angle from the horizontal. And then if your wall is somewhere here, then this is now your failure plane. So, but they are just the same. Okay. So depending on where's the location of your failure or your retaining wall, either this side or this side. Okay. Okay. So that is with respect to the Rankine's active earth pressure coefficient. Okay. So this time we now have the Rankine's passive earth pressure coefficient. Okay. So again, here we have the soil mass. Okay, you have the soil mass with the wall here AB, but this time the wall is moving towards the soil. Okay, so that means you have a passive state. Okay, you have the you can we can call this condition now the Rankine's active. Rankine's passive state. No, wherein the wall is moving at the deformation of delta L. Okay, so comparing now the more diagram or the more circle for the active and the passive earth pressure conditions. So again, at an at-rest earth pressure condition, you can consider here the Mohr circle A, this one here, just the same as what we have seen here, the same A. So that is now your, this is now your sigma sub O prime, and this is now your um, uh, case sub sigma sub H prime, no, which is equal to K sub O times sigma sub O prime. Okay. Now, if the wall will move towards the soil, okay, then the horizontal earth pressure in the soil mass will increase, no? Because they will tend to get pressed. Okay, so the earth pressure, the horizontal earth pressure will tend to increase. So unlike in the active state, wherein the horizontal earth pressure uh, will decrease. Okay, here now in the passive earth pressure, the horizontal earth pressure will increase to a certain passive earth pressure at this point. Okay, so that's the difference. Okay, so then you now have your failure more circle here, B, more circle B. Okay, wherein you can now have your failure envelope. Okay, so considering the derivation that we have followed for the active earth pressure condition, then yeah, the for the active earth pressure um, derivation, then the results is just basically the same. No? So if you look at the formula here for the passive earth pressure um, formula, it's just the same as the active earth pressure actually. Okay, but the only difference is that in the active earth pressure you have here, I think minus. I think yeah. Okay, so everything here is minus, minus, and minus for the active earth pressure condition, while for the passive earth pressure condition you have here plus, plus, and plus. Okay, that's the only difference. So please take note of that. So then we now call this the Rankine's passive earth pressure. Okay. So again, for cohesionless soils, C prime is 0. So if C prime is 0, so everything here will be gone. So then you only have this term here, which is, this one now here. So this is now your gamma C. Okay. Then if you take the ratio of gamma sub P prime over gamma sub O prime, okay, that's the passive earth pressure over the overburden pressure. This one here, over O, that's overburden, that's O, okay. Um, then that's equal now to K sub P, okay. Um, where K sub A is the coefficient of Rankine's active earth pressure coefficient. Okay, so that means K sub P is equal to the tangent, the square of the tangent of 45 plus 5 prime over 2, whereas K sub A is equal to the tangent, square of the tangent of 45 minus, that's minus, okay? So that's the only difference. K sub A is minus, K sub P is plus. Okay. Yeah. For the Rankine's active and passive earth pressure conditions. Okay. So take note here. In the case of the active earth pressure coefficient, this is minus, but the slip planes have an angle of plus. No? Okay. A higher angle of slip plane. While for the passive earth pressure condition, you have here plus, but the slip planes make an angle of 45 minus 5 prime over 2. No? So that means the failure planes are flatter. They are flatter with respect to the horizontal plane. So that means if your wall is here, then this is now your failure plane. If your wall is here, then this is now your failure plane. Okay. Okay. So let us now consider, okay, a case wherein you have a backfill. Um, then you have a cohesionless soil with a horizontal ground surface, which is okay. In practice, this is usually the case. Okay. So then let us consider two cases again, the active case and the passive case. So we now have here for the this is now the active case, and this is now the passive case. Okay, wherein for the soil you have now the unit weight, the friction angle, and then the or the effective friction angle, and then this one is your effective cohesion, which is assumed to be zero. Okay, because you have a cohesionless soil, and then you have a horizontal ground surface. Okay, so in that case, yeah, then here we can create the pressure diagrams. Okay, the pressure diagrams, which are both triangular for both the active state and the passive state. Okay, so here the maximum value in the or the maximum pressure in this earth pressure diagram is equal to um, K sub A times the effective overburden pressure, sigma sub O prime equal to gamma H. Okay, where this is now your H. Okay, so that's the earth pressure at this depth H. Okay, so this is now your maximum active earth pressure. Okay, and then the total force, the total active force per unit length of wall is now equal to 1/2 K sub A times gamma H prime, or that is just equal to the area of this pressure diagram. Okay, that's 1/2 H times this term here. Okay, which will give you H squared. Then the location of the force is just the centroid, which is the centroid of the triangle, that's h over 3. Yeah. And so again, here you have the failure, the slip plane. Okay, if the wall is moving away from its original position, then the slip plane can have an angle of 45 plus 5 prime over 2. Okay. So compared to the passive state, this one here. Okay. So here in the active state, this is your failure wedge. In the passive state, this is now your failure wedge. Okay, wherein it creates an angle of 45 minus 5 prime over 2. Okay, but the pressure diagram is just the same as the active state, but only that here the maximum pressure is equal to K sub P times the overburden pressure, which is equal to gamma times your H here. Okay, this is now your sigma sub O prime. Okay, because uh, K sub P is equal to sigma sub P over sigma sub O prime. So sigma sub P is then equal to K sub P. I hope you're seeing my cursor. K sub P times sigma sub O prime, which is equal to gamma, the unit weight times 5H. And then for the passive earth pressure, or the sorry, the total passive force per unit length is now equal to just the area of the pressure diagram, which is equal to one half H times this term, which will give you this one here. Okay, one half H times the passive earth pressure. Okay. So that is the case for a backfill with a cohesionless soil with a horizontal ground surface. Now we also have the case wherein we have a backfill. Okay. I still assuming a horizontal surface, but this time you have a partially submerged cohesionless soil, say granular soils, for example, which is normally what we put when we do backfills, unless we don't have a choice with cohesive soils. But this time it supports a surcharge, wherein the surcharge can be anything. It can be an equipment, it can be a house, or any structure. So this is now the figure for that one. Okay. Okay. So you now have here your wall, your vertical wall, okay, of a height h. But then let us now try to break it into two, into h1 and h sub 2, where h sub 1 is the depth of the groundwater table. Okay. Then for um, uh, the soil above the groundwater table, you have the unit weight and as well as the friction angle. Okay, so there's no cohesion. It's zero because it's a cohesionless soil. And then below the groundwater table, you have the saturated unit weight because it's saturated below the groundwater table. Then you have also the friction angle here. The cohesion is zero because you have a cohesionless soil. These are usually granular soils. Okay. But here at the horizontal surface, you now have a surcharge load of Q. Okay, surcharge load of Q. Okay. So in this case, first, let's consider the active case wherein the wall moves away uh, uh, from its original position. So hence the slip planes is 45 plus 5 prime over 2. Okay. So so to derive now the total active force per unit length of wall, okay, then we just sum up. We just sum up the area of the total pressure diagram. Okay, wherein if we recall again the um, active earth pressure is equal to the active earth pressure coefficient multiplied by the overburden pressure. And that can be your O, that means overburden. Okay. So to get now the total force, so again, we just need to get this, the sum of all the pressure diagrams. Okay. So to do that, let's see here. Okay. So you now have here the pressure diagram. Okay. So I think what he did here is okay. So initially you have the the pressure here at depth zero is not zero, no? Because you have a surcharge. Okay, so that means at the surface the pressure is equal to the surcharge times the active earth pressure coefficient. No, that's this one here at the surface. Okay. Now, at a depth h sub 1 or until the groundwater level, okay, so then you now have the surcharge plus the active earth pressure equal to K sub A, okay, that's equal to K sub A times the overburden pressure, okay, or the overburden stress equal to the unit weight times H sub 1. And that gives you this amount here, okay? Now, at the bottom, let's say at H sub 2, okay, so at the bottom, okay, so from the groundwater level, from the groundwater level down to the bottom of the wall, you have here H sub 2. So that's, so there, the pressure will now be equal to this one, plus the additional the additional effective stress. Okay, additional effective stress equal to K sub A times the effective unit weight times H sub 2, this one here. Okay, where the effective unit weight is equal to the saturated unit weight minus the unit weight of water. Okay, and then that's the effective stress part with respect to the source. And then for the poor water pressure part, okay, because you have the effective stress plus the poor water pressure. So the poor water pressure is equal to the unit weight of water multiplied by H sub 2. Okay. Okay. So if you want to get now the total force, so let's try to sum up the pressure diagrams. Okay, so let's try to sum up this pressure diagram here. Okay, which is just equal to this pressure diagram plus this pressure diagram. Okay, so to do that, you can do it in many ways. But here, what he just did is um, he for this term, what he did is he considered this pressure diagram. Okay, please observe my cursor. He considered this pressure diagram. Okay, that's your one. Okay, that's your pressure diagram one until here. Then your pressure diagram two is this triangle here. Okay. Then the third pressure diagram is this rectangle, the remaining rectangle here. That's the third pressure diagram. Then the remaining triangle here is the fourth pressure diagram. Then this is now your fifth pressure diagram. So that's why you have here 1, 2, 3, 4, and 5 terms for your pressure diagram. Okay. So the first pressure diagram is K sub A times Q times H. No? So that is actually this rectangular, no? A rectangular pressure diagram. No? That's a K, that's Q times K sub A times the total H. No? Because H sub 1 plus H sub 2 is H. Okay? So that's this one here. So that gives you this term. Okay. So next, this is just the pressure diagram of the triangle. This one here, which is equal to H sub 1 half of H sub 1 times K sub A gamma A sub 1. That's this one. Because originally that's a Q K sub A. So the remaining term here, the remaining value is actually K sub A gamma A sub 1. Okay. So that gives us this pressure diagram. Okay. This one, area of this pressure diagram. And then the next pressure diagram is this triangle, this rectangle here. wherein this rectangle is equal to k sub a gamma h sub 1, that's this one here, multiplied by h sub 2. Okay, that gives you this value here. And then this 1 half k sub a gamma prime times h sub 2 squared is actually the area of this remaining small triangle here, which is equal to 1 half h sub 2, that's h sub 2 here, times this is the remaining value here, because this one here until here is equivalent to this value. So the remaining value here is equal to k sub a times gamma prime H sub 2, where gamma prime is saturated unit weight minus the unit weight of water. And then plus the area of this pressure diagram, which is equal to 1 half H sub 2 times this um, earth pressure here, this lateral earth pressure here equal to, sorry, this poor water pressure rather, which is equal to the unit weight of water times H sub 2. And that gives you 1 half unit weight of water times H sub 2 squared. Okay. So that is now the total force per unit length of the wall, okay, for the active, Rankine's active state condition. Okay. For the Rankine's passive state condition, considering this scenario, okay, Um, so basically, the derivations is just the same, only that here, instead of sigma sub A, you have sigma sub B for the passive state. Then you have here the passive earth pressure coefficient. Okay. So with that, if you can, if you compare now the total active force and the total passive force, okay, then if you can see here, it's just everything is just basically the same. The only difference is that here you have k sub a, here you have k sub b, k sub a and k sub b, k sub a, k sub b here, then k sub a, then k sub b here for both the active and the passive earth pressure conditions. Okay. Okay, this might look lengthy with respect to the formula, but basically, if you have values here, then this is just a short formula. Okay. Okay, so I think we still have some time for some problem solving. So just bear with me because this will be our last meeting, I think. Okay. So for the remaining sessions, my colleagues will just give you some exercises prior to um, your final exams. Okay. Or if you have some further questions or clarifications, you can probably ask my colleagues as well. Okay. Okay, so we have here an example just taken from your book. Okay. So here you have here this figure. Okay, considering a 4.5 meter high wall. Okay, wherein the groundwater level is around 3 meters. Okay, from the ground surface, which is horizontal, and then the bottom of the wall is around 4.5 meters. So, so these are now points A, this is now point B and point C. Wherein here you have a sandy material. Okay, wherein you have for the sandy material, we assume it to be a cohesionless material, for example, wherein the effective cohesion is 0. The friction angles are 35 degrees. Okay, but the unit weight is equal to 15.7 kilonewtons per cubic meter above the groundwater table, whereas the saturated unit weight is equal to 19.2 kilonewtons per cubic meter below the groundwater table. So take note, the saturated unit weight is higher than the unit weight. So this is probably dry or moist unit weight, which is not being specified. Okay. Um, so here, the condition is that the wall is restrained from yielding. So that means the wall cannot move. So that means we have at-rest earth pressure conditions. Okay. So then we are now asked to calculate the lateral force PO per unit length of the wall, and we're also asked to determine the location of the resultant force. Okay. So here we are given the OCR value for the sandy material equal to 1.5. So with that, we can probably use the formula for the at-rest earth pressure coefficient K sub O. Using this formula, I think this is according to Callaway and Main. Okay, so with this formula, we are given the friction angle equal to 35 degrees. Okay, that's this one, 35 degrees. Um, Multiplied by the OCR value equal to 1.5. Then here you have 35 degrees. Okay, so just substituting values, then we have the at-rest earth pressure coefficients equal to 0.538. Okay. Now, since there is no surcharge, so at depth Z, okay, at depth C here, since there is no surcharge load, at depth C, the overburden stress is equal to zero. The horizontal earth pressure or the horizontal effective pressure is zero, and the pore water pressure is zero, no? Because it is above the groundwater level. So at depth 3 meters, then you can now have an overburden stress equal to the depth 3 meters. Then that's the height multiplied by the unit weight of the soil, which is 15.7. Okay, that's your overburden stress. Okay, that's equivalent to this value here. Then for the horizontal effective pressure, you just multiply the overburden pressure by the at-rest earth pressure coefficient, which is this one. Then that will give you this value. Okay. And then here at this depth, the pore water pressure, at this depth, the pore water pressure is still zero. Okay. Now at depth Z equal to 4.5 meters. Okay. So the effective overburden pressure, okay, or the effective vertical pressure is equal to is equal to 3 times the unit weight of the soil plus 1.5 times the since this is now since the soil is now below the groundwater table, then here we consider the effective unit weight, okay, which is equal now to the saturated unit weight 19.2 minus the unit weight of water, which is now this one here, 19.2 minus 9.81, which will now give us this value. Okay. And so for the horizontal effective pressure, okay, we just multiply the overburden pressure by the at-rest earth pressure coefficient to give us this value here. Okay. And so at depth 4.5 meters, we have a pore water pressure equivalent to 1.5 meter depth times the unit weight of water, which gives you this one here, that gives you this value. Okay. Okay. So yeah, just to illustrate the pressure diagram. So we now have sorry, we now have the pressure diagrams here. So this is now 25.34. That's basically this one here. Then you have 39.92 and then 14.72. So that's 25.34. That's 39.92. And then this is 14.72. Um, I think this is an error, type of error. This is a 4.5. No, that's not 15. Okay, this is depth. Okay. So to get now the total force per unit length of wall, so we can probably add the pressure, all the pressure diagrams here. Okay. So take note here at depth 0, the value is 0. No? Okay. Here. So that's equivalent to this one. That's 0. Then here also at depth 3 meters, the pore water pressure is 0. So that's why here you have 0 as well. Okay. So to get now the total force, then we just sum up the pressure diagrams here. Say for this pressure diagram 1, 2, 3, and 4. Okay. So for the pressure diagram 1, that's just 1/2 of 3 times 25.434. That's basically, that's 1/2 of 3 times 25.34. This one. Okay. Then plus the area of this rectangle, that's a 1.5 times 25.34. Okay, that's the area of this rectangle here. Okay, that's 1.5 times 25.34 plus um, the area of this triangle. That's 1/2 of 1.5 times this length here, which is 39.92 minus 25.34. That's this length. That's equivalent to 14.58. Okay, that's this one here. And then plus the area of this pressure diagram, which is 1/2 of 1.5. Okay, this is 1.5 times 14.72. Now that gives you this one here, this pressure diagram. So just sum up all these things. That gives you now the total force per unit length of the wall, which is 98 kilonewtons per meter. Okay. And so to locate now the resultant force. Okay, so we just sum up moments of the pressure diagram um about point C here. Okay, we just sum up moments about point C at this point. So then that gives you um, this one here. If you sum up moments, you have the force times the distance. Okay, so the resultant force here is 38. 38. Then the distance of that force is actually um, from point C, no? From this point C, that's 1.5 plus the centroid of this triangle, which is 1/3 of 3. So that's a 1.5 plus, that's 1.5 plus 1/3 of 3. That's the centroid of this force, which is 38.1 with respect to C. And then for this force here, for this pressure diagram 2, the force is 38.1. And then the centroid from point C here is 1.5 over 2. Then for this resultant force here, for this triangle, which is 10.94, okay, for this triangle, that's 10.94. That's a 1.5 over 3. And then finally, you have the resultant force for this triangle, which is 11.04 times its centroid with respect to point C here. Okay, point C, that is 1.5 over 3. Okay, that's the summation of moments of pressure diagram about point C. Then divide that by the total lateral force, which is 98. Okay, then that gives you um, a location of 1.76 meters above point C. So that's if this is 1.5, so that's somewhere around here. No, 1.76 meters, somewhere here. Okay. Okay. Okay, so we now have here another problem. Okay, so you now have here a 5 meter high retaining wall. Okay, this one here. You have a 5 meter high retaining wall. Okay, with sand material, a normally consolidated sand material with an OCR equal to 1. And then this granular material has a unit weight of 14, and then a friction angle of 30 degrees. Okay, and then a equation of effective equation of zero, because it is, yeah, considered equationless material. So we are asked to find the Rankine active force per unit length of the wall and the location of the resultant, as well as the Rankine passive force per unit length of the wall and the location of the resultant. Okay. So for part A, since the effective equation is zero, okay, so then we can use this equation here for the um, active earth pressure, which is equal to the active earth pressure coefficient times the overburden pressure, which is equal to the unit weight times the depth, z. Okay. And then k sub a is equal to 1 minus sine phi prime over 1 plus sine phi prime. Okay? So that means k sub a, if you just substitute the given, which is 30 degrees, the friction angle, okay, so that gives us 0.33. Okay. Um, so that means at depth z equal to zero, the active earth pressure is zero. Okay, because yeah, there's no surcharge there. Okay. But at depth C, okay, at depth C equal to 5 meters. Okay. If you see my cursor at Z equals to 5 meters, then we can now use this formula. Okay. So that's the unit weight is 14, the depth is 5, then the active earth pressure coefficient is 0.33. Okay. So that gives us an active earth pressure of 23.1 kilonewtons per cubic meter. Okay. So the pressure diagram for that is this one here. So you have here now the active earth pressure at a depth of 5 meters equal to 23.1. So to get now the total force is just equal to the area of this pressure diagram, which is 1/2 times 5 times this value will now give you this value here. Okay. And then the resultant is just 1/3 of this height from this point here, which is 1.67. Okay. Now for the passive force, okay. So yeah, again, we can use, since the effective equation is zero, then we can use this formula here. Okay, it's just basically the same as the active earth pressure, but only that here you have the passive earth pressure coefficient, where the formula is just the same as the active earth pressure coefficient. The only difference is that here you have minus and plus, but here you have plus and minus, which will give you a value of 3. Okay. So normally, if you have a friction angle of 30 degrees, normally we already know that the active earth pressure coefficient is around 0.33, and the passive earth pressure coefficient is already 3. So actually, we already know it by heart, no? Based on practice. Okay. So with that, at the ground surface, the passive earth pressure is zero. Okay. Because this is zero and you don't have surcharge. But at the depth of 5 meters at the bottom of the wall, then you now have the depth of 5 meters here times the unit weight of the soil times the passive earth pressure coefficient equal to 3.0. Okay, so that gives you this value. Okay, so the passive pressure is roughly about, yeah, about 10 times, about 10 times the active earth pressure, because of their earth pressure coefficients, which is about roughly 10 times also. Okay. Um, so for the total passive force, so again, it is just equal to the area of this pressure diagram, which is just equal to 1/2 times 5 times 210. Okay, which will give you this value here. And then the centroid is about 1.67 meters, which is just 1/3 of 5 meters. No? The centroid of the triangle. So that gives you these values here. Okay. Okay. So I guess that's the end of my slides. So, do you have any questions or clarifications so far? Okay. Okay, let me just stop share so I can see if there are some questions.
Hello, excuse me,
Okay.
sir.
Yes. Yeah. I think this is our last meeting. So yeah, you can ask questions. Yes, of course. Okay. Yeah. What advice and insights can you give us, aspiring CEs, to guide us toward a successful and fulfilling career? Okay, so as a seasoned civil engineer, what advice and insights can you give us as far as is to guide us toward a successful and fulfilling career in our field? Okay, oh, this is a very interesting question. Um, okay, um, I think as of the moment, I think your main goal, your main goal is, yeah, to first to pass the board exam, to pass the board exam. Just like how I advised my son. But my son is also a civil engineer. He also graduated from the University of San Carlos, I think around 4 years ago. I think. Yeah. So I always tell my son, okay, I think first things first. Okay. So the moment, try to pass the board exam first. That's your main goal. Okay. Now, after you pass the board exam, okay, then you already have your license. Okay, then you can already sign plans. Okay, you're already um, registered, by law to sign some plans. Um, if you want to proceed to a structural field, structural engineer, then you can sign structural reports as well as structural plans. If you want to proceed to a geotechnical practice, for example, just like what my son is currently doing, he's doing some freelance geotechnical work where he is now also licensed to sign geotechnical reports in that case under my guidance. Okay, so it depends, no, on your interest. Okay, normally here in the Philippines, many would proceed to structural design, although there are already a lot of structural designers in the Philippines. Um, there are some geotechnical engineers as well, but there are also other fields of civil engineering. Okay, you can go into water engineering, or you can go to construction management. There are a lot. No, there are a lot. For example, in the company I'm working with, as of the moment, if you try to look at that website, you can see there are a lot of uh, skills where a civil engineer can work. Okay, such as a cost engineer. No? Okay, a cost engineer, a planning engineer, a safety engineer, we normally prefer, okay, it depends on the work, no? Especially we on the civil side of things. Okay, we always prefer civil engineers, no, to act as the cost engineer, the planning engineer, or the safety engineer for that aspect. In construction, you always have these three basic roles. No? Okay? If you don't want to go into the design side, no, such as the water design engineers or geotechnical engineers or structural engineers, you can go to the construction side. In the construction side, you can be a construction manager, a cost engineer, a planning engineer, a safety engineer for that matter, especially in large construction companies. Now, I'm currently working in a quadruple A contractor, which is only a few here in the Philippines. I think there's only about less than 10 quadruple A contractors in the Philippines. That's why we are one of the selected contractors building the Cebu Cordova Bridge project. Okay, so with that, you basically have a lot of your in your plate. No? Okay, so my only advice is whatever your interest is, maybe you can try to specialize with that. No? Okay, try to specialize. Okay, um, if you want to proceed to structural engineering, okay, try to proceed to try to have more studies in structural engineering. If you want to go to other fields, um, try to do further studies in such field of specialization. No? I'm actually teaching also in the master's degree program in the Polytechnic University of the Philippines here in Manila, where I am teaching geotechnical students, okay, as well as railway students. No? Okay. In a PUP, for example, they have a course there specializing on railway. Yeah, because here in Manila, we have railways, and now we are doing subway projects. Hopefully, in the near future, we will like now be Singapore, wherein if you come to Manila, you will now be traveling by subways. No? Okay, to ease the burden of traffic, something like that. Okay, so just try to do things one step at a time. Okay, just do things one step at a time. Okay, as of the moment, the only thing I can advise is just try to pass the board exam first. Okay, and then you will have a lot of time to think of other things if you still want to specialize um, after you have finished the board exam. Okay, because in my experience, you will have less opportunities if you don't have a license. Okay. Normally, companies would prefer licensed civil engineers. In my case, we were just lucky. No? We were just lucky during our time that we were offered graduate programs. When I was still teaching there full time, no? At the university about 10, 12 years ago. For the last 14 years. We were just lucky that at the time we were given offers to do a master's degree studies and a PhD degree studies, um, which were made available to us. During the time, nobody in the department was yet thinking of a master's degree or a doctorate degree. That was a foreign word. No? For the University of San Carlos, it was a foreign word to us, to both faculties and students, because no one attempted to do a graduate studies program. It was only during our time wherein some of us faculties attempted no, or had the courage to proceed to a master's and doctorate degree programs. Okay, and then after that, we were just quite lucky. I must say, lucky. It's not easy. It's not easy to do graduate studies. I'm just a bit lucky because nobody was able to guide us much on that aspect. Unlike now, no, you're a bit lucky right now. I must say. Okay, being students of University of San Carlos, you're a bit lucky because many of your faculties are already going into that aspect also. No? So some of them are doing master degree programs, PhD degree programs. I think I think there are about four, I think about four, three, four faculties of the university whom I have recommended, who asked for my recommendation when they proceeded to a PhD degree program abroad, no, in Canada and some in other countries. Because normally, when you proceed to a graduate program, you will ask for recommendations from people who also have masteral and PhD degrees. Usually, the universities will ask for it. No? For example, I think Engineer Maguyon, when he proceeded, I don't know if he still um, s- um, met with him, but before he proceeded his PhD program, yeah, he asked me that, sir, if you can kindly give me a recommendation because I'm planning to proceed to a PhD program in Canada. Okay. Although Engineer Maguyon was also quite lucky because he did some research under my field. No? Okay. I guided him with his master's degree, what to do in his master's degree. And that he proceeded. And in Canada, for example, that research is a bit hot topic, still a hot topic. And so when I recommended his PhD studies, I did not have difficulty making my recommendation because in that recommendation, you have to explain why you are recommending this person for such a degree. Because you can imagine you will be offered scholarships, and these are not small amounts. Okay, when you study abroad. Um, in my case, when I studied my master's degree in Europe and my PhD degree in Japan, this I did not spend a single centavo. These are all scholarship programs. Okay, so the the competition is quite tough. Okay, so that means you have to think of something that can or that is helpful. No? That would be helpful. For example, if you want to go further research, okay, you must think of something or some topics that will be helpful to the country because that's that's the main concern that they will be asking. For example, when we applied for the Mumbu Kagakushu scholarship in Japan, or in short, the Mombushu scholarship, okay, uh, the first thing they asked me during the interview is, what can your research do to our country? How can it help our country? And yeah, during that time, I was just lucky because I was trying to understand landslides at that time. Okay, because during that time we had when I went to Japan, we had the famous landslide in Leyte. For those of you who are from Leyte, no, from Ginza Ogun Leyte, the southern Leyte, no? I don't know if you can still recall that. That was about 12, 13 years ago, 14 years ago, where many died. The whole town was submerged. Okay, and so I tried to defend that. Okay. So these are things that you can think of, okay, if you want to do further research. Think of a topic that can be essential to our country, not to their countries, no? Like not to Japan, not to Europe, because they already full of research there for their own countries. But think of something that can be helpful to our country. In my case, I think this is one way that I'm trying to give back to my university, no? Because if not for San Carlos, I cannot have my master's degree and my PhD degree. Okay, so whenever the university asks me to teach again as part time, of course it's part time. I can never ignore the university. I'm always there at their disposal because I owe my um, advanced degrees with the university. Then, sir, I hope I have answered your question. Okay, okay, thank you, Denzel. Do you have any other questions? Okay. So again, this is our last meeting. So please ask me any questions you have in mind. Okay. Okay. I guess there are no more questions or clarifications. Just hope I just hope that my lectures are clear enough for you. Okay. I hope my colleagues can explain in more detail during the exercises with you. Basically, what I have discussed here are just some basics. Just some basics of geotechnical engineering. Geotechnical engineering is still quite a broad field. Okay. But at least on the undergraduate level, you have some basic knowledge of uh, the basics that we usually apply in practice. And basically, some of the things here that I have shared with you, we are actually using this in practice until now. Until now, we are using this in practice. Okay, even in the Cebu Cordova Bridge project, when I reviewed the design reports from the foreign designers, we are still applying these concepts in that Cebu Cordova Bridge that is standing there in front of you. Okay, so I hope um, they are clear enough for you. Okay, so I guess if there are no more questions, it's already 9 o'clock. Okay, so again, thank you everyone for your time and good luck with your other subjects. And also good luck to my colleagues who can probably share more no? With their experiences as well. Okay, and with respect to this subject. Okay, have a nice evening, everyone. Thank you very much.
Goodbye and
Goodbye
thank
and
you,
thank
sir.
you, sir.
Goodbye and thank you, sir.
Goodbye and thank you, sir.
Goodbye and thank you, sir.